Okay, welcome back, everyone. So our first speaker today is Song Hee, and he's going to tell us about surfaceology for string and particle amplitudes.
Thank you. First, I'd like to thank the organizers for the invitation to this really wonderful meeting, including the adventure yesterday. Since I had not been stuck in the desert, so I will like to share with you some new progress on understanding scattering amplitudes, both for particles and their UV completion into the string amplitudes. And this will not be based on things you're familiar with, for example, like Feynman diagrams for particle scattering or the worldsheet CFT for the string scattering. This will rather be based on something that's fundamentally combinatorial. So we want to study some combinatorial problems for curves on the surfaces, which is, of course, related to the worldsheet of the string scattering, but thought about in a completely different way. So basically some integrals over the curves on the space of these surfaces. And this will be based on works with Nima and three really outstanding students, Chi, Jing, who is in the audience, and Carolina, who gave a talk last streams. And also with some other follow-up works with my other collaborators. Okay, so the big picture here is that over the last decade and even a longer history, that we've seen a lot of structures that's geometrical and more precisely combinatorial underlying scattering amplitudes and also other physical quantities in quantum field theory. And these things looks like polytopes. You know, there are some d-dimensional objects where if you go to a boundary, it's a d-1 dimensional object and so on. There's this boundary structures. And the most famous one actually goes back to the modular space of n-punctured Riemann surfaces of genus G, which of course is crucial for both the conventional string and also twister and ambitwister strings. So I like to point out that why this string and the twister string amplitude give us correct factorization and so on crucially depend on this combinatorial structure of the modular space. And in the last 10 years or so, there's this object called positive Grassmannian, which has basically been responsible for a lot of magics in this special theory, planar n equals 4 super mUs. So these structures, this combinatorial structure, all live in some auxiliary space, okay? But more strikingly, there are a theme that we start to find this geometrical and combinatorial objects, these polytopes, directly in the kinematic space of our scattering data. So for example, the famous example is this amplitude, which describes you the all-loop integrands of the scattering amplitude in planar n equals 4. Surprisingly, the reduction, the dimension reduction of this guy to 3 dimension give you the all-loop, another geometric object called ABGM of amplitude, which give you all-loop integrands in this theory. And you can also go off-shell. Actually, there's been works, very recent works, revisiting this problem of 4-point correlators, Hall-BPS correlators in super mUs. Its integrand also given by some geometry, which can also serve as the integrand for energy correlators and so on. But these are more or less related to the positive Grassmannian world. How do this modular space magic play directly in kinematic space? This all starts with our work in 2017, which studied the simplest colored scalar theory called Chase phi cube. That will be the star of this talk. There's a surfaceology polytope, very famous polytope living in the Mandelstam space, which give you the volume form of this polytope give you the Chase phi cube amplitude, and it's closely related to another surfaceology known as the Deligne-Montfort compactification of the M0n. And this has been generalized to all loops in a series of work over the past 5 years. That now we understand that to all order in the 't Hooft coupling expansion, the amplitudes in this simplest Chase phi cube theory is described by some polytope called surfaceology. And behind it, there's also some stringy objects, which describe you bosonic string amplitudes, whose field theory limit give you the Chase phi cube amplitude. So this will be the main thing I want to talk today. There are, of course, other extensions to cosmological background. There's the very recent work on cosmohedron for the wave function of the correlator in this Chase phi cube theory, which give you some polytope for the cosmological observables. And I like to point out this viewpoint is very useful for studying finite integrals, even for studying like Mellin amplitudes in de Sitter and so on. There's some new positive geometries waiting to be explored there. So this is a one-slide summary of what I'm going to talk about today. It's basically, as I said, a new way of thinking about particle or string amplitudes just based on combinatorial. I told you there's polytopes, which give you the phi cube amplitudes. But there's also the stringy extension of these polytopes. So for example, at tree level, you will find that the famous, what you guys are most familiar with, the Koba-Nielsen integral, is actually a most natural string completion of the associahedron. So this is not by studying the worldsheet vertex operator and so on, but rather by studying something called U variables on these surfaces. So these U variables were actually first used in the earliest days of the dual resonance model, but later people given up on it but switched to the worldsheet coordinates. But actually, it turns out that there's a counting problem which allows us to write down to all genuses the U variables. And this point of view, called curve integrals on the surface, has been very useful in many aspects. Already at tree level, this allows you to see the manifest factorization. You don't need to do any blow up on the worldsheet variables, but directly see that on any massive residues, what are the residues on any massive level for this stringy bosonic string tree level amplitudes. And at loop level, there's also a lot of understandings which I won't have time to get into, but at least in the alpha prime to 0 limit, it's very useful. It's very easy to extract this limit, and this limit gives you, in principle, the all loop cuts in this theory, and also if you want to include other interactions, the all loop cuts and based on the cuts, the all loop recursion can be constructed for these theories. Okay? And of course, there are profound connections with a lot of new areas of mathematics. Very surprisingly, you may think that this is all for this toy model, trace phi cube. Okay? So why do you care so much about trace phi cube? Very surprisingly, this toy model, actually, this stringy trace phi cube amplitude, this curve integrals, contains realistic theories. At least for colored particles, now we understand that all loop amplitudes of pions and gluons, the gluons being the non-supersymmetric Yang-Mills, not the n=4 super Yang-Mills, in arbitrary space-time dimension, they are contained in this stringy trace phi cube amplitudes. You just need to shift your kinematics to a different point. I'll get into this in a moment. So at least at tree level, you already see that there's a unification of phi cube, pion, and gluon tree amplitudes, which also directly generalize to all loop pion amplitude in nonlinear signal model. So we can literally see that the all loop pion amplitudes are contained in trace phi cube amplitude without stringy. This is already at field theory level. Now, for string level, for gluon, you will really need to study the all loop stringy trace phi cube amplitudes in order to extract the gluon amplitudes out of it. So we'll see that there's some kind of scaffolding gluons, where each gluon is represented by a pair of scalars to be extracted from 2 endpoint trace phi cube amplitude, your endpoint n gluon Yang-Mills amplitude. And there's actually qualitatively new features of all these theories reviewed by the picture. For example, after all this years study, we didn't really know that there's all these zeros, not only for phi cube, but same zeros in the kinematic space, some locus in the kinematic space that tells you phi cube, pion, and gluon amplitude vanish. So these are about the study of the zeros of particle and string amplitudes, and their factorization behavior near those zeros. So this will be one example of the new features we discovered using this new formalism. So let's look at this theory. So this is the simplest colored scalar theory with this phi being n by n matrix. So you can use the double line notation and have this fat graphs with the genus expansion. So this is an example of tree level 5-point graph, which is dual to a disk with 5 punctures, and there's a particular triangulation associated with this Feynman diagram. Okay, this is a fat graph, and this is a 1-loop 4-point graph due to the disk surface is due to the 1-loop box diagram. So the kinematics of the kinematics we introduce on these surfaces are different from usual external or loop momenta squared. This is actually, at tree level, they're very similar. So for every curve you associate with some kinematic invariance, at tree level, this will just be the sum of this momentum on either one side or the other. But at loop level, you see that there are infinite number of these curves. So physically speaking, in the end, you identify them, go back to the physical kinematic space. But on the surface, they are distinguished, okay? So in principle, you are dealing with infinite number of curves with infinite number of kinematic variables associated with them. But at tree level, it's simple enough. You just deal with every diagonal of your angle. There's a planar variable xij associated with this diagonal ij. And our usual Mandelstam variable pi dot pj is given by this familiar combination of the planar variables. So at tree level, many years ago, we already understood that the tree amplitude, which is summing over all triangulations of the angon, is given by this volume of the association, volume form of the association, where you really take all this planar variable to be positive and intersect it with a subspace. Okay, so this is 4 and 5 point examples of the trace phi cube amplitude. Now we switch gears. So actually, this is all field theory, and there's generalization to all loop with very complicated surface hedron story, which I won't get into. But now let's see how to UV complete it. So this actually goes back to the first formula, that the Veneziano amplitude and its Kobayashi endpoint generalization, where instead of considering tachyon, we shift the kinematic, so it's all massless scalars with the price to pay is this factor, most natural factor for the ordering, the Park-Taylor factor, Z12, Z23, and so on. So this formula is very familiar, but the way we look at this string amplitude is to introduce these U variables. This U variable is also very, the earliest days of string theory, you already see this is some special cross ratios on the disk. But once you introduce these U variables, it's very natural to see that, oh, the Kobayashi factor becomes all the product of over all the curves, where for each curve you have U variable to the exponent of the X variable I introduce you, okay? So this will allow you to generalize to all surfaces. Of course, the Park-Taylor factor here requires something else. You need to give me a set of independent variables. The U variables are not independent. They are one for each curve, right? You need to give me n-3 independent positive parameterization, and this is also naturally given in terms of surface triangulation. So you have this d log form, dy over y, and then some counting problem that tells you how u is expressed as some ratio of positive polynomials of y, and you take this product over all u to the x, okay? So even at tree level, let's look at this new formula. Why is it more useful than the original worldsheet formula? It makes all the factorization completely manifest. So by factorization, I mean you go to a special, you go to some position where one of the x equals 0 at field theory limit, or equals some non-negative integer at, for finite alpha prime. Whenever that happens, the integral is localized by this corresponding u variable of that curve goes to 0. But this equation tells you, because all the u are between 0 and 1, this is a positive space with ordering, once this uab goes to 0, every u variable crossing it, the so-called incompatible u variable, all goes to 1. Okay? So they decouple from the system. The system immediately factorizes into two lower point amplitudes. So this is for any massive level, you will see that the factorization, you don't need to start to blow up all the z coordinates. And this is, of course, for 4 point, it's just an example that goes back to the beta function. And at tree level, as I said, this is a string extension of the association, but the really cool thing is that now you can define the u variables and this positive parameterization for any surface. So you have a stringy formula for any surfaces whose factorization manifests, and field theory limit becomes easy to extract, which give you trace phi cube amplitude. Okay? So I would like to also to emphasize that this way of thinking about the bosonic string is more in the positive world of hyperbolic geometry of the corresponding Teichmüller theory, as opposed to our usual way of thinking in the Riemann surfaces with complex structure. Very good. So we've seen this phi cube string. We've seen some stringy integral, not just for tree level, that give you trace phi cube, and there's all loop extension. What can you do with it? What new things you can learn? One thing is that we learned that there's there are really infinite number of zeros, and near each zeros there are some splitting of the amplitudes. For Veneziano amplitude, of course, you know that s plus t equals any non-positive integer makes the beta function vanish. So this is well, non-zero. Actually, most of the zero we study in a different language is already now more than 50 years ago. But now we understand it very nicely that if you look at the rectangle worth of the C variable I told you, the Mandelstam, pi dot pj set to 0, this makes the whole amplitude vanish. Actually, field theory limit, you send this C to 0, but for finite alpha prime, you can send them to any non-positive integer. You can easily show from our new formulation that there are this many infinite families of zeros for the string amplitude. And more surprisingly, what if you turn one of the Cij on? If you don't send them all to 0 or all to integer, you turn on one of them to be generic, this string amplitude just factorizes. It's factorizing into an upper amplitude, a lower amplitude actually with shifted kinematics, so they are really be thought of as two currents times the 4-point bridge in between. So this implies some field theory, interesting field theory splitting that if you send most of the C's in this rectangle 0, but turn on one of them, you see this very nice factorization. And of course, that explains the 0. If you further send the last C to 0, this prefactor, 4-point prefactor, would vanish. Now, this is for phi cube. But here's the punchline that if you deform your amplitude, this is the phi cube amplitude, dy over y u to the x. If you deform it by this special factor, you get to the real world. you immediately get pion and gluon scattering amplitude out of phi cube. So this is just kinematic shift. I'm shifting all my x even, it is a 2n point amplitude. I'm shifting all my kinematic variable x even by a amount alpha prime delta and odd by the opposite amount. I'm not touching any even odd. Just this simple shift. The key is that it preserves all the Cij. The Cij is invariant under this shift. This is the only shift that preserves all the Cij. So it will preserve all the zero and splitting. So historically, this is actually the opposite way we find it. We find there are at least 3 theories sharing the same zeros and factorization. So we wonder what's the mechanism responsible for it. It turns out that they all come from the same string integral with different kinematic shift, which keep the Cij intact. So I told you delta equals 0, no shift, this is phi cube. If you shift delta to any non-integer value in the alpha prime to 0 limit, this integral, later you will see that the field theory limit gives you the pion amplitude, tree amplitude. If you shift it by integer amount, it's more subtle. It changes the singularity structure. If it's plus or minus 1, it gives you this 2n scalar amplitude coupled to gluon. So this is where you first see gluons. You start with 2n phi cube amplitude, do the shift at integer like 1, you get this. You can also shift to other integers, then you get, in addition to this scalar coupled to gluon, they start to couple to higher spin particles, of course. But we will focus on this Yang-Mills scalar theory. So all these 3 theories are unified in the same function. Just evaluate at different kinematic points and take alpha prime to 0. This is already, this will explain the zero and the factorization that I just mentioned. So I like to expand it a little bit that this splitting near the 0 is actually something very, very general. So it universally holds for almost all the scalar, this special effective field theories that we know of, like nonlinear Sega model, there's the double copy of it to give you special Galilean and dBi and so on. But also it directly works for particles with spin, gluon and gravitons, in either bosonic string or superstring, okay? So here's the picture. The general picture, so we're taking a very, very quick detour away from the surface. I'm describing it in the usual language to be more familiar with. So you pick 3 particles, and the rest of the particle divided to blue and red. You set all the SAB, where A belong to red and B belong to blue, to be 0. This is the splitting picture. So this is still something we understand from string picture, but we don't quite understand from directly from field theory. Why all these field theories obey the same splitting behavior when you send this momentum, Lorentz product of momenta in these 2 sets to be 0. From string, this is literally just the splitting of the Kobayashi-Nielsen factor, and it explains our original factorization near 0. And very nicely, in this paper, they explain that for the phi cube and nonlinear Sega model amplitude, you can also generalize it to all surfaces. So all higher loop things satisfy the similar splitting if you consider them as gluing surfaces. But I just want to mention one more thing, that when you apply it to spinning particles like gluon and gravitons, there's very beautiful splitting of bosonic open string or closed string, either in bosonic or superstring case. So because here everything is tree level, so it's very easy to study also superstring, that this simplest skinny splits where we send only smallest number of Mendel sum to 0 already implies the soft theorem, either for gauge theory or gravity. And for the effective field theories, they imply the enhanced Adler theorem. Of course, if you study more general splittings, you start to see some multi-soft theorem, which I think is very interesting to explore further. Okay, so let's go back. So I already told you that nonlinear second model is containing stringy trace phi cube. But when you take field theory limit alpha prime to 0, since this delta is a generic number, it's not an integer, it's equivalent to take the delta to infinity. So that is why we can go back to field theory without talking about stringy phi cube. Just give me a field theory phi cube amplitude. If you shift in this way and send delta to infinity, so you kill all those poles you shifted, you immediately obtain the nonlinear second model amplitude. So this works for all loops. Okay? So we found something very interesting that to all loop order, once you compute the trace phi cube field theory amplitude without any stringy deformation, take this limit, delta to infinity of the shifted field theory amplitude, you get all loop integrand in nonlinear second model. So this is something very interesting you can understand from Lagrangian point of view, that why the pion Lagrangian can be thought of as this shifted trace phi cube Lagrangian. So it applies to any physical quantities. Now, this is essentially now the second part of my talk where you really want to face the challenge of getting gluons. Okay? So for scalars, you can do it in many ways. You take trace phi cube, you can deform it to any colored scalar, or you can shift it to get pion as a very special case. But for gluon, it's really difficult because you're shifting the delta to be an integer. So it really changes the singularity structure that you cannot directly get Yang-Mills scalar amplitude out of the trace phi cube. You have to consider the full bosonic string. So let me explain this first. The 2n point bosonic string amplitude, if you go to a very special kinematic point where the kinematic limit, where only the 1, 2 pair, 3, 4 pair, 5, 6, only this pair of epsilon dot epsilon is non-vanishing, this gives you already this shift, okay? So it's just a different way of writing things that we pull out the Park-Taylor. This is the stringy trace phi cube. I told you the bosonic string for scalars at tree level. Now, shifted by this ratio, which is exactly U even by U odd. So this picture is telling you what? It's telling you if you start with 2n scalar bosonic string amplitude, you shifted by this, you shifted kinematics, it's giving you n pairs of scalar amplitude where each pair is actually coupled to a gluon, because this is starting from higher dimensional gluon in bosonic string. So this is what I call scaffolding. The scaffolding is really telling you that to express the momentum of a gluon, you need a sum of the two momenta of the scalars. And the polarization of the gluon can be described, for example, as the difference of these two momenta. So eventually, to extract the n gluon amplitude out of the 2n scalar, you need to take this limit that the gluons are on shell. Okay? So this is a very simple explanation of why this delta equals 1 give you n gluon amplitude out of 2n phi cube amplitude shifted, right? So more concretely, you take this some triangulation which include this n gong inside the 2n gong, we call it scaffolding triangulation, and each of these on-shell condition produce you a gluon. So you're sitting inside a 10-point phi cube amplitude, there's a 5 gluon amplitude sitting inside. You need to take these residues, and in the stringy formula, you take the residue and take alpha prime to 0. For example, if you start with a 6 scalar amplitude, take these residues, there's nothing left, there's no integration left. And you're localized to 3 gluon amplitude, the first term being the Yang-Mills amplitude, now written in terms of the 6 scalar kinematics. So this is a new way of expressing the epsilon and the momenta of the gluon. And this is the F cube term. So this captures the 3-point bosonic string when you scaffold to give you gluon amplitude. So how do you see some very important properties of gluons, such as gauging invariance and factorizations, directly in this variable? For example, for gauging invariant, it's really telling you that there's this expansion of the n gluon amplitude into this object. This combination ensures that it's multilinear in every epsilon and invariant when you shift epsilon by the amount of momentum. So this is the gauge invariance statement. And very nicely, using the U variables, you can directly prove this. So the whole string, whole 2n scaffolded string amplitude satisfies this. So it must be gauge invariant. It also has to factorize correctly. We already said that the phi cube amplitude factorizes correctly, but that's exchanging a scalar. Now you change the dy over y into dy over y squared. That's the shift that does. This y squared, when you take residue, acting derivatives on the cobalt-Nielsen produce you this exchange of gluon. So this is the gluon exchange. Between left and right, there's this, you can imagine this written in terms of epsilon. It's really just the gluon exchanged between them. Okay, so this immediately generalizes to all loops. Because you can think of as tree level, there's this dy over y trace phi cube. You change the dy over y into y squared. It introduces you, for every pair of phi cube, every pair of scalar, there's a gluon, there's a spin 1 massless particle here. So this picture must be very general. You can start to look at trace phi cube at higher genus surfaces and do the same change of variable, do the same shift, sorry. So for example, at one loop, concretely at one loop, you take the 2n point trace phi cube, bosonic string amplitude. Here in principle, there's the infinite product of u to the x because there are infinite number of curves. But you just change dy over y to dy over y squared. In practice, so you also need to worry about there are some self-intersecting curves and this closed curve enclosing the loop puncture. In practice, we don't need the full-fledged string thing. We just take the alpha prime to 0 limit. This already gives you all loop Yang-Mills integrand. One check you can do is on this leading singularity. You can take residues, take enough deep enough residues, and the answer is given by gluing 3-point amplitude I just told you. They gluing them together at loop level, and they all work. So this formula as a generating formula of all loop gluon leading singularities. Okay? So of course, it also extends the notion of gauge invariance to, and also the unitarity cuts and so on to higher surfaces. In order to completely prove this proposal, we still need to study the actual integrand. So here is just there's enough check about the general property and the leading singularities. So how do you go to the, how do we determine the general, the full integrand? That's still a very difficult task. Because of this dy over y squared at higher genus surfaces, how do you take alpha prime to 0 limit? It becomes very difficult. But luckily, we have a better way for practical purposes just to express all the cut of loop integrand in terms of forward limit of cheese. So this is a very old idea, but for non-supersymmetric case, this gluing of the, for example, the tree level amplitude will take these two gluon to be at L and minus L and then glue them together. This famously produces you 1/0 issues, right? But the surface kinematics give you a way out. So the surface kinematics, remember I told you, it includes all the variables for tadpole, for bubble on the external legs. They all now live in the surface without sending them back to the physical kinematics. They are all well-defined variables. So at this surface variable level, surface kinematics level, I can safely take the forward limit of chi to get one loop and keep going. So this is a solution to, at the moment, we don't know how to take alpha prime to 0 limit of those integrals I told you, except for leading singularity. So instead we study its residues and reconstruct the whole integrand. But the surface kinematics already provides you a way of regulating everything and give you a perfect integrand. This integrand has no 1/0 issue and so on. You can check it out on the surface. It also has gauge invariance on the surface sense, and all this cut that when you either cut it to factorize into a lower loop amplitudes with a gluon exchange, or you cut the loop open, as I said, to become forward limit of lower loop things. So you can use these cuts to reconstruct the whole surface integrand. And of course, this thing gives you a huge expression already at one loop level. It's a perfect integrand that includes all the variables. If you want to get a physical integrand, you can discard all those tadpole or massless bubbles. So it becomes a very practical way of computing Yang-Mills higher loop integrand. There are even checks against the integrated result of helicity amplitudes and so on. Okay, so this becomes a still work in progress of making this all loop recursion for pure Yang-Mills work. But let me end with some comments on how to include matters. So actually, there's very nice work for the colored Yukawa theory that in the sense of similar to how you get general colored scalar case, including them in the surface language. But what about fermions in the loop? So here I'm using the surface just as a tool of taking the forward limit. We know very well that if you have tree-level amplitude with n gluons and an additional pair of particles, either a pair of gluon or fermion, there's a very nice expansion into this gauging invariant building blocks times some mixed amplitude with scalars. We use the surface language to help us taking the forward limit. So if you have a gluon line or fermion line, you just glue it to form a loop. And the prefactors also naturally become the loop level, but becomes the chase, either the Lorentz chase or the spinor chase of these few strings. So in this language, already for the pure Yang-Mills, you get a beautiful one-loop expansion. The n gluon amplitude is expressed in terms of scalar loop object times this multiplied by this gauging invariant building blocks. But you don't need to do any work to go to spinor case. Go include the fermion case, because the fermion loop has exactly the same building block. You just change this Lorentz chase to a spinor chase. Okay? So for any gauge theory, general gauge theory, you always have this expansion of the universal building, one loop, scalar loop building block, multiplied by this combination of chase V or chase S. These are the gauging invariant things. And we interpret this result as some kind of SUSY word identity in play for one loop. For example, if you literally apply it to maximal super Yang-Mills case, you will see the famous no triangle property and so on, so that the formula makes it manifest that the maximal SUSY case starts with a box and so on. So that all being said, we still don't understand how to introduce well-sheet fermions in this surface language. So already at tree level, there's a beautiful translation of the original superstring formula for n gluon in this scaffolding language. Now you can see that the superstring surface integral starts with the bosonic string. The bosonic string is the simplest term in this surface language. And now you have corrections. You have other correction terms that changes the bosonic string. And the job of this correction term is really ensure the well-sheet supersymmetry. For example, you can check that all this leading singularity, I told you there's gluing of 3 point. The 3 point consists of Yang-Mills and F cube, but all the F cube will immediately get canceled if you introduce this SUSY correction terms. So of course, we still don't know how to generalize this idea to all the loop level. For example, to see within the loop or the SUSY cancellation as a correction to the dy over y squared bosonic string case. Since I'm almost out of time, I'll just summarize here that by giving some outlooks, I think there are many things to explore in the future, especially this all-loop recursion for Yang-Mills is a very useful tool, but we haven't touched the gravity, right? So everything I talk about apply to colored particles, and at tree level or even at the all-loop leading singularity level, you can easily square it to get this scaffolded gravity. But the true challenge lies in extend this curve integral to colorless case, not to this this positive geometry of the worldsheet, but really to complex case. And how do you make all this non-planar factorization and cuts also manifest in those cases? And there's the extension to superstring and extension possibly to so there's already polytope for wave function. Can you now, just as you did in flat space, deform such polytope into some curve integral in de Sitter space, or as well as for the ADS correlators? That would be very, very interesting to explore. Okay, I'll end here. Thank you.
All right, thank you, Song. Now we have time for questions. Daniel?
Hi. So I guess this trace phi cube theory, it doesn't make much sense physically, right? It's
a toy model.
Yeah. Yes. So you could make it more physical by having quartic terms. So,
yes.
But I guess one of the quartic terms is multi-trace. It's trace of phi squared, quantity squared.
Sure. So
how much of what you said can still be done if you have quartic terms?
Very good. So the part where the part where you can derive tree amplitudes and loop integrands for amplitudes using this curve integral applied to any colored scalar theory. So you just have to change it from very simple dy over y into more complicated things. But the part that this full integral as a UV completion really give you bosonic string and so on will not work for those things. So trace phi cube is still very special in the sense that you write down the most natural curve integral whose field theory limit give you trace phi cube. That turns out to be bosonic string if you have the product over all the curves, infinite number of curves. You can still cook up these formulas just like what the Brown group did for the Yukawa theory. You can cook up similar formulas for the quartic interaction and so on. It's very, very easy to write down. But what's the string formula behind it is still unknown. Yeah, that's special for trace phi cube. And for similar applied to our Yang-Mills case, we deform the dy over y square. At tree level, it's just a bosonic string with gluon, external gluons. But at loop level, it's no longer bosonic string. It's something else. So in this sense, the Yang-Mills is another example of introducing this quartic interaction. It's still unclear to me how to make the formula really about strings for this general case. But for trace phi cube, there's both ways will work, finite alpha prime and the alpha prime to zero limit. Yeah. Of course, everything I'm talking about here are either integrands or formally integrated amplitudes, right? It's perturbation expansion. So that's in that sense, it doesn't make much difference you study trace phi cube or other colored scalar theories. Yes.
Okay, more questions? Julio?
I have one question here. If you do the shift in the kinematical data at the level of the canonical form, would the alpha prime corrected canonical form also have an interpretation as a volume in kinematic space?
Good question. So for trace phi cube, all the field theory limit of this curve integral I introduced has a polytope interpretation. That's because, that's also partly related to the last, why trace phi cube is special. It only has logarithmic singularities. It has a chance to be in volume of something. It's like 1 over a lot of denominators. Now for general scalars or for pion, for gluons, you have numerators, right? So once you deform it, the job of the deformation is essentially produce you those correct numerators, which factorize for spin 1 particle and so on. They won't have any interpretation as volumes, So as I said, everything I talk here in full generality is combinatorial. Only when you study like trace phi cube, when you go to field theory limit, it has a polytope geometrical interpretation. Those are very special. So trace phi cube can be viewed as the version of n equals 4 super amuse in this world, in this d-dimension amplitude world. It only has logarithmic singularity. But our deformation away from trace phi cube to gluon and so on can be viewed as going to more realistic theories. Now you have lost the interpretation of a polytope or geometry, but luckily you still have the combinatorial, the counting problem on the surfaces to help you get there. Yeah, that's the main message. Yeah.
What about gravitons?
Yeah. So you basically, if you literally try this game, it will. So, okay, there are two ways. So from what Nima and Julio and the collaborators, they are doing, the trace phi cube integral immediately contain those colorless, like sigma cube interactions. So those colorless cases, just like closed strings, is contained in when you go to study open string factorization and so on. So here, the trace phi cube story allows you to expose to those colorless scalars. But there's a different question is how you get really to gravity, not just colorless scalars. So can you study our Yang-Mills all loop integral and see gravity out of it? That I don't think work, because the Yang-Mills integral is not the full string integral. It's just a way that gives you correct the field theory limit. So we have no idea how to make gravity naturally appearing in this Yang-Mills integral. Yeah.
I just have a broad question. Now that you guys are able to do these non-supersymmetric theories, do you see any actual phenomenological applications of these methods arising in the near future? I
mean, that's at least the one thing I mentioned is that this all-loop recursion, you really want to put it in a practically usable form. Because in this way, it depends on all these surface kinematics, many variables. Once you discard all the scaleless integrals, For example, we can compute this two-loop six gluon amplitude in full generality, in general dimension. That would potentially would be something very interesting. But you need to go to the physical kinematics to really put it in use. You need to perform also, of course, all those loop integrals. I mean, this is all about getting the correct loop integrands for pure gluon case. And of course, the inclusion of fermions is also important. So that's why we're exploring this loop recursion as a byproduct from this study. You really just want to construct the loop integrands in general gauge theories in this way. Eventually, maybe this recursion way will be more efficient than other method. Right now, it's still at early stage.
I think in view of time, let's thank Song again.
Thank you.
And now we're going to move to the next speaker.
Okay. My slides are already here. Let me try the point.
Okay. Our next speaker is Lorenzo Di Pietro, who is going to tell us about exploring confinement in ADS.
Okay, thank you. Thank you very much to the organizers for this opportunity to present my work. It's really been a wonderful conference. So my seminar today is mostly based on a paper we wrote last summer in collaboration with Riccardo Ciccone, Fabiana De Cesare, and Marco Serone, with the same title. And the topic of this work is quantum field theory on the background of anti-de Sitter space. So I would like to start by explaining why I think this is an interesting background to study quantum field theory. So these are not new ideas. They appeared many times already in the literature, at least starting from this work by Callan and Wilczek back in 1990. And just to set the notation, I wrote here the metric of ADS that I will use. I will always be in Euclidean signature. And Z is the usual radial coordinate with conformal boundary at Z equals 0. And L is the radius of ADS. So the first reason why ADS is an interesting background is because the radius L functions as an IR regulator. It cuts off the large fluctuations in the IR of quantum fields, and which often are the reason why the theory is difficult to solve. And we can use it as an additional parameter to interpolate between the UV and the IR of the quantum field theory, so to probe the theory at different scales. So this, of course, is not at all special of ADS. It would hold in any background in which we have some scale, like, for instance, a periodic box. But the advantage of ADS is that we can do that while being maximally symmetric. So we have the same amount of space-time symmetries that we would have in flat space. So basically, we introduce this IR regulator while not paying any price in terms of space-time symmetries. And OK, you can also say that this would be also common. For instance, if we put the theory on the sphere, we would have the same logic. But at the same time, ADS has also the nice feature of having an infinite volume, which means that quite a few interesting field theory phenomena are visible, which require infinite volume, for instance, symmetry breaking and phase transitions. So related to this last point, if we go at infinity in ADS, unlike on the sphere, in ADS we can define interesting asymptotic observables simply by considering correlation functions of operators inserted at the conformal boundary, which are somewhat analog of scattering amplitudes for field theory in flat space. And of course, as it's very well known from the ADS-CFT correspondence, and it's also true here, the isometries of the space act as the conformal group on these conformal correlators. So basically, for any quantum field theory, if we put it on this background, we get for free a boundary conformal field theory. And the data of this boundary conformal field theory are fixed in terms of the bulk couplings of the quantum field theory. And they also depend on the choice of boundary conditions. So this is all very similar to ADS-CFT, but it's important also to stress the differences. So the important difference is that Since in this case we are considering a rigid background, we don't have dynamical gravity, in this boundary conformal field theory we will not have a stress tensor. And another important difference is that this boundary conformal field theory should be thought of as just a subsector of the theory, just a subset of all the observables. There is no duality in this case. Okay. And the particular setup I would like to apply this to is the case of asymptotically free theories. So we imagine that in the UV we have some description in terms of some massless degrees of freedom, which are weakly interacting with each other with some small coupling G. And however, in the IR, the theory goes to strong coupling and develops some mass gap, which we can imagine proportional to the dynamically generated scale. And then the idea is to vary the ADS radius and interpolate between these two different regimes. And a nice feature is that in some case, one can argue that there must be a sharp phase transition as we vary the radius L between these two regimes. And this phase transition is detectable in some drastic change of the boundary conformal field theory. So this gives us a nice opportunity in this setup, which is to study carefully the boundary conformal field theory, for which we can use all the wonderful modern techniques in CFT. And understanding how this behaves, we can use it as a way to detect, or perhaps ambitiously even explain the emergence of the mass gap in the limit of large radius. Okay, so this is the idea. Okay, having explained the idea, this is the outline. So we start by reviewing a paper from 2012 by Roni, Berkuz, Tong, and Yankelevich. Some authors are here in the audience, in which they consider Young-Mills in ADS4, and they argue that there is one of these transitions of the type that I just described, which is in this case a confinement-deconfinement transition. Then I will consider, so I will review this paper from 2023 that I wrote in collaboration with Christian Copetti, Ziming Ji, and Shota Komatsu. And motivated by this confinement-deconfinement transition, we studied some toy models in 2 dimensions to understand better the nature of the transition, and like, for instance, sigma models. And the nice thing in this toy model is that you have an additional computational handle, which is the Largen limit. And finally, I will go to the more recent paper. And in this more recent paper, what we did is to simply use perturbation theory, starting from the G = 0 free limit, to get some hints about the nature of this confinement-deconfinement transition. Okay, so let's start from the paper of 2012. So they made the following observation. If we start with a very small ADS in units of the lambda Young-Mills scale, then the UV Lagrangian is a reliable description of the theory, and nothing can stop us from imposing a Dirichlet boundary condition for the gauge fields. This is the Dirichlet boundary condition. So as a result, we have non-abelian conserved currents in the spectrum of boundary operators. And this means that the gauge group of Young-Mills becomes a global symmetry of the boundary CFT. And this is, of course, the very familiar statement from ADS CFT that if I have a gauge symmetry, it becomes a global symmetry on the boundary. On the other hand, if we assume what we believe to be true for the theory in flat space, we immediately see that this picture cannot remain true for arbitrarily large radius, because this current should disappear. It should disappear for, you can say it in 2 ways, either because since there is confinement, there should not be any colored asymptotic state, and this current would give a colored asymptotic state. Or equivalently, you can say that since a mass gap should develop, then all the dimensions of the boundary operator should become parametrically large in this limit in which we send L to infinity. And a current has a protected dimension, which is 2 in this case of 3 dimensions, so it can certainly not give rise to a gap spectrum. So for all these reasons, we expect that the current should disappear. And okay, so the simplest thing to imagine is that we have one transition between this deconfined phase with currents on the boundary and the confined phase at large radius. And so I would like to emphasize that now proving the disappearance of this boundary condition that we see at weak coupling, in my opinion, is really like the key to understanding confinement and the emergence of mass gap from the point of view of ADS. And so, unfortunately, today I will not claim to have proved that, but we will try to make some progress in this direction. And so motivated by this, we will try to understand better what happens at this transition, okay? So in the paper from 2012, they brought up some possibilities for how this Dirichlet boundary condition might disappear. So one thing one can imagine is there is some Higgs phenomenon happening. So perhaps some composite of the gluons gives us some bulk charged scalar, which at some point condenses as we go to strong coupling. And what is the translation from the point of view of the boundary CFT? This would mean that, of course, the data of the boundary CFT depend on the radius. So it would mean that as we increase the radius, at some point, a certain adjoint operator becomes of dimension 3. And this is the correct dimension to appear on the right-hand side of the current conservation. Okay, so this would mean that the current can stop being conserved and get lifted. Okay, this is one reason why the current might start disappearing. A second possibility that they called decoupling is, for instance, we can imagine that simply at some point the gluon states become null as we go to strong coupling. And this would signal the sickness that make us transition to the new phase. This also has an interpretation in terms of the BCFT. It simply means that the coefficient of the two-point function of the currents becomes 0 at some critical value of the radius. And another possibility that they imagined is a tachyonic instability. Okay? So this means that, again, there is some scalar in the bulk, perhaps, again, some composite of the gluons, which at some points has a mass which is below the Bretton-Friedman bound. It is a bit less obvious what is the sickness in this case in terms of the boundary CFT, but if one thinks about it for a second, so the reason why it's not obvious is because having mass equal to the Bretton-Friedman bound simply means that the dual operator has dimension 3 halves, and in principle there doesn't seem to be anything wrong with that. But then, at least if you are at weak coupling, and indeed this Bretton-Friedman bound, it usually applies when we have some weakly coupled scalar. So if you are at weak coupling, then we can take the square of this operator, and we see that it becomes of dimension 3. So we get a marginal operator, which is singlet under all the symmetries. And so this operator can start running and destroying the conformal invariance of the boundary condition. So by studying these 2D toy models, we were motivated to generalize a little bit this third possibility, so without making any reference to weak coupling. And we propose what we call marginality, which is simply that the possibility for the transition is that at some point a singlet scalar operator in the boundary CFT becomes marginal. And then when it becomes marginal, we need to check its beta function, so we need to add it to the boundary action and check if it runs and if we can get a fixed point. This is necessary in order to preserve the isometries of ADS. And this paper by Loria, Milam, and Barris actually exactly considered this setup, in which we have our bulk Lagrangian and this marginal operator, and computed what is the beta function of this boundary marginal coupling. You see here we have to compute in a perturbation around the point, which is a strongly coupled point, in which the operator became of dimension 3, which is what I call here this G critical. Okay, I'm using interchangeably like varying the radius or varying the coupling, because I'm imagining to consider the coupling at the scale of the radius of ADS. So we need to deform a little bit away from this critical value of the coupling, and we find this form of the beta function. Okay? So there is a contribution coming from the bulk and a contribution proportional to the coupling itself. So the nice thing that you see is that this is precisely the form of merger and annihilation, meaning that for G square smaller than the critical value, we find 2 zeros for this marginal coupling, meaning that we have actually 2 ADS invariant boundary conditions. However, as we increase the coupling across the critical value, these 2 CFTs, the terminology is that they merge and annihilate, so they become some complex fixed point, and as a result, this boundary condition disappears. Okay, so based both on the 2D toy models and on the perturbative data that I will present, I claim that this appears to be the most likely scenario for why the Dirichlet boundary condition disappears in Young Mills. So now let me briefly explain the 2D toy models. So in order to discuss 2D toy models, we need to find an analog transition in 2D. So in 4 dimensions, it was this confinement transition. What could be an analogous phenomenon in ADS2? So we have an analogous phenomenon if we consider theories in the bulk which have a continuous global symmetry. And then what happens is that when the radius is very small, often we can impose boundary conditions that give rise to spontaneous symmetry breaking in ADS2, and so they give rise to some massless scalars. However, we know from Coleman-Mermin-Wagner theorem that this symmetry breaking phase cannot survive all the way to infinite L, because in flat space these Goldstone bosons cannot be present. So we have a similar setup in which we need to transition from this symmetry breaking phase with gapless degrees of freedom to some gapped phase where the symmetry is preserved. So these are the toy models that we considered. And we considered various examples, but the simplest one is just the ON sigma model in ADS2. So this is just the theory of the n scalars constrained to live on the sphere. And the spontaneous symmetry breaking boundary condition amounts to taking the vector field and setting its radius to be some constant non-zero value, capital phi, at the boundary of ADS. Okay? So this is the spontaneous symmetry breaking boundary condition. And then, without giving you any details, I will just tell you what you find by solving at large n this model. What you find is that, indeed, for sufficiently small value of the radius of ADS, you find a solution of the gap equation, which has a non-zero radius phi at the boundary. And so you are in a symmetry breaking phase. And the mass of the vector fluctuation is 0, it's constant and 0. Now, as you increase the radius, this value of the radius of the sphere, so there are 2 radii here, this is the radius of the sphere, shrinks. And until you reach the transition point, which is precisely, in this case you can check, is of order of the dynamically generated scale in this sigma model. And nicely enough, you can compute the spectrum of ON singlet marginal operators. And you see that precisely at this point, indeed, there is an ON singlet operator which becomes marginal. So in this case of dimension 1, because the boundary is a CFT1. And so like in this marginality scenario that I explained before. And then if you go on the other side, what happens is that you start developing a non-zero mass for these vector excitations, and you have a symmetry preserved phase. Okay? So in all the examples we checked in 2D, it was always the case that at the transition we would get an operator precisely of dimension 1. Okay, so now let's go back to the more recent paper. So here we make a very humble step towards understanding this transition, which is just to check what happens in perturbation theory. So let me remind you of these 3 scenarios. So the marginality scenario required a singlet scalar of dimension 3. The Higgs required an adjoint scalar of dimension 3. And then there was this decoupling scenario, which required Cj to become 0. So what we're going to do, we're going to just compute these 3 observables around the g equals 0 limit and see which one is more in danger, let's say, to reach the critical value. Okay, that's the simple idea. So for A and B, I should tell you which singlet scalar and which adjoint scalar, because of course there are going to be many. But the leading candidates are the lowest dimensional one. And in this case, you see, at 0 coupling, the boundary theory is just a mean field theory of this conserved current. And the leading operators in the singlet and adjoint channel are just double traces bit out of the current. So I'm going to have this singlet operator and this adjoint operator. They both start from dimension 4, because the current is dimension 2. And so our question is whether they can become of dimension 3 due to the anomalous dimension. And I should also specify that in the particular case of SU2, actually, since this coefficient DABC turns out to be 0, actually the leading adjoint operator start from dimension 7. So in the case of SU2, it's already clear that the Higgs scenario is quite unlikely. And in order to test C, what we're going to do is just compute the first correction to this two-point function coefficient. OK, so without further ado, let me just tell you the results. So these are the results for the gauge group SU and C. These are the numbers we get. So a few comments. So all three of these we just got by doing width and diameter calculations in ADS. To avoid confusion, this is the with anomalous dimensions. This is just the constant gamma of Euler. It's not an anomalous dimension. And you might notice that these coefficients here have some resemblance with the one-loop beta function of Young-Mills. And that's not a coincidence, because actually for this particular entry, we have also an independent way of doing the calculation, which I don't have time to explain in detail, but it's based on doing conformal perturbation theory around the free point. And in that approach, you can actually see very transparently the relation between the one-loop beta function in the bulk and this anomalous dimension. And so the main lesson to be drawn from these things is that the anomalous dimension of the singlet is actually the largest coefficient. And being the largest coefficient, this means that the singlet operator is the one that is most in danger to become marginal as we increase the coupling. So which is in agreement with also the lesson that we took from the 2D toy models. And we can entertain ourselves in doing some estimates by truncating this expansion at next to leading order. And if you do that, these are the values of that you find for the critical coupling, in which this dimension, these observables reach the critical value. And so it's clear that the marginality scenario, the one in which the singlet becomes marginal, is the favored one. It's also nice to notice that if you include this factor of 16 pi squared, which typically arises from perturbative calculations, the critical value that we get is not so big. So it might suggest that this perturbative result is kind of reliable. OK, so before moving to the conclusions, I also want to mention that there is another interesting boundary condition that one can consider, which is the Neumann boundary condition. So in the Neumann boundary condition, the difference is that all the way from weak coupling to strong coupling, we have still a gauge symmetry on the boundary. So as a result, all the operators, all the physical operators need to be color singlet at all values of the radius. So in that case, there is no reason to expect any sharp transition. So we can expect continuity. And this nicely matches with the other considerations we are doing, because if we check in that case the lowest singlet operator, which turns out to also have dimension 4, and is given by this trace FF with the built out of the boundary gluon, if you wish. So if we consider the anomalous dimension of this guy, we see that actually it's positive. So it goes away from the marginality point, which suggests that indeed this boundary condition can very well be continuous all the way to strong coupling. So this is the image that summarizes this scenario that emerges. So here there is our coupling, which we can form this dimensionless combination. And then we have here the Neumann boundary condition, which, as far as we can tell, seems to be continuous all the way to flat space. And instead, the Dirichlet boundary condition, what seems to be the case is that at some critical value, it merges and annihilates with another boundary condition, which we can call D star. At the moment, the nature of this other boundary condition that merges with the Dirichlet, it's not very clear at weak coupling. So we don't know what is the origin of this D star from weak coupling. But that's what seems to be happening. OK, so let me summarize. So we studied transitions from gapless to gapped phases in ADS. And first, we went through some solvable examples in 2D, and they seem to point to merger annihilation as the most promising mechanism for the disappearance of the gapless phase. And then we showed some perturbative results for the Yang-Mills that point in the same direction. So there are some interesting future directions here. So to go beyond perturbation theory, what can we do? So one thing we can do is to try to apply a numerical conformal bootstrap to this boundary CFT. So now the technology of the conformal bootstrap is developed enough that one can indeed study impulse crossing symmetry on the 4-point function of 4 non-abelian conserved currents in 3 dimensions. And so with this gentleman, we are now considering the possibility of trying to corner the boundary condition of Yang-Mills. And the hope is that we will be able to get some rigorous bounds on these 3 interesting parameters. Another thing one can consider to go beyond perturbation theory is to promote to the supersymmetric version of the theory. In particular, if one considers n equals 2 version of the theory, n equals to super Yang-Mills in ADS4, then it turns out that there is enough supersymmetry preserved by the boundary condition that we can still do localization, for instance, and get exact results. And we can consider the simplest case, which is just the SU2 case, Seiberg-Witten theory. And in this case, there is a similar story in which we expect that there is a transition. This time, the theory will not become completely confined, but there will be a transition between an SU2 phase at small value of the radius and a U1 Coulomb phase at large radius of ADS. And this is something that we're exploring with these authors. And that's all. Thank you for your attention.
Thank you. Now we have time for questions. Shiraz?
If you were to heat these theories up, you put them at finite temperature, do I understand right that in the Dirichlet case, you would have an n square phase, a deconfined phase all the way down to 0 temperature up to a critical radius, and then the phase transition would happen, and you'd have the deconfinement temperature would go up to lambda QCD.
Yeah, I think there is going to be an interesting 2-parameter phase diagram, and yeah, presumably there will be, so this transition point will move as you change the radius of the S1, but so
it will be deconfined all the way down to 0 temperature for a while, and then rise?
I think so, yes.
On the other hand, in the Neumann case, there would be a phase transition at order RADS, and then just rise. Is that right?
Sorry, a phase transition? Why a phase transition? At 0 temperature, there is no phase transition.
You have quarks or not? No quarks, just pure Yang.
Yes.
So in that case, you've got a Gauss law. So say we are at large n. In the Neumann case, suppose we are at large n.
Okay.
And then you'd have a phase transition between a phase which is order 1 at low energies, order n squared high energies, even at weak coupling.
Okay.
And then that would just rise in temperature. Is that what it is?
Well, I was expecting that it would be order 1 always in Neumann because of the singlet constraint, because all the operators are going to be singlet of the color group.
Well, you could say the same on a sphere. And on a sphere, we know there are phase transitions.
Okay. But do you
Gauss
agree that
law, important, not important kind of phase transitions.
But you agree that in this case, all the boundary operators are going to be singlet, right?
Same on a sphere.
Okay.
Gauss law forces everything to be a singlet. But it becomes unimportant.
Okay, we can discuss this.
More questions?
Can the framework of quantum field theory guide us toward the quantum theory of gravity?
Well, I mean, that's a quite broad question, but I think, yes, certainly quantum field theory is useful in the approaches we know for quantum gravity.
Regarding your last slide, could you comment when you do the numerical bootstrap, how would you fix your position along the, how do you input your, the radius in this setup?
Well, what you can imagine doing is, so first of all, you can imagine doing some bounds just on CJ, like trying to see, so there are basically two structures appearing in the 4-point function of the currents. I mean, in the exchange of the current itself, there are two structures that can appear, and then you can basically separate them in one which is CJ, one which is an angle, and then you can scan this angle and try to find the minimal possible value of CJ. So that's just by itself. And then you can also do plots in which you have these two things will appear as dimensions of the exchanged operators, and this will appear as the OP coefficient. So you can do plots in this two-dimensional parameter space. You can try to do exclusion plots. But if your question, maybe I guess your question is, how are you going to know about the radius of ADS? Yes. Yeah, so that indeed, it's not immediately clear. So you can do plots as a function of CJ, but we don't know for sure that CJ is monotonous in the radius. It might be that something can be proved regarding the relation between CJ and the radius, but yeah, we're not sure about that.
Just one here. If we focus on just on QCD, there are other models regarding confinement, like where they use a Shigar shape geometry, and could this approach also be used to more highlight on this chiral symmetry breaking and other stuff?
Well, for chiral symmetry breaking, one thing you can do is that you can consider the generalization in which you include the quarks. So there is a nice feature if you include quarks that in anti-de Sitter actually turns out that already at very weak coupling you are forced to break the chiral symmetry just to the vector subgroup, because you cannot have the boundary condition can only preserve some non-anomalous subgroup of the flavor symmetry. So in that case, like let's say that chiral symmetry breaking is really in your face, you have it already at weak coupling. But yeah, that's the only comment I can make at the moment. We didn't study much the theory with quarks.
Okay, thank you.
Thank you. Let's thank Lorenzo again.
And,
thanks.
Right, and our next speaker is Julio Parra Martinez, who is going to tell us about exact tidal anomalous dimensions.
Okay, well, first of all, thanks a lot to the organizers of this spectacular conference, and to Ahmed in particular for inviting me to give a talk here. I'm going to tell you about some work I've done with these great collaborators, Misha, Yuezhou, and Zihan, who unfortunately are not here. And the title is Tidal Anomalous Dimensions, which I'll explain what it means in a second, but let me start by motivating the setup and the basic questions that we're concerned with in this talk. So my talk is related to the following question: how do we tell apart, say, a black hole from some other object of comparable size and comparable mass? But I'm going to put some restriction, which is that we can only probe it at wavelengths larger than its radius. Okay, so frequency is much smaller than the inverse radius, so we cannot really resolve the object. Okay. What could this object be? Well, at previous string conferences, we've heard talks about maybe we want to distinguish a black hole from something like, maybe it's a small black hole and a very heavily excited string. Maybe we can ask the question, well, how different is a black hole from just some chunk of matter, like a piece of coal or a neutron star? Or, okay, for the people who are kind of starting their PhD, what's the difference between a black hole and the infamous quasi-spherical cow? Okay, this example is because actually what we are going to use is what I think it's the simplest effective field theory, which we learned in undergrad, where we replace whatever object that we have by a point particle. Okay? So all of these things we can just think of as a point particle, maybe with some spin. So there's like a whirlline action, which we know very well. This is the relativistic version coupled to gravity. Maybe there's some terms that depend on spin, and then there's going to be corrections. So my talk is about these corrections to this point particle behavior. Okay, so let me describe in more detail the structure of this effective field theory. So we have the leading term, which is the mass of the object, or its energy, if it's a more complicated composite object. There's a leading term, which is kind of the coupling of the angular velocity of the frame which is attached to the object to the spin of the object, which I'm calling L, right? And then there's the multiple moments of the object. That's what I said. This is the simplest EFT in undergrad. It's just the multiple expansion of the object, but these multiples generically are going to be dependent on, they're going to have some dynamics which can be more or less complicated. Okay, so here I'm showing the electric quadruple, the magnetic quadruple. There's also kind of magnetic version. So E is kind of the electric part of the Val tensor. There's a corresponding coupling with a B, which is the magnetic part. And then there's some terms with some undetermined Wilson coefficients that are at spin squared, and they're essentially like the spin-induced multiple moments. Okay? And these multiple moments encode whatever microscopic degrees of freedom we have for these different objects. So for the black hole, it's okay, whatever is the dynamics of the black hole, the kind of near horizon scale, maybe even quantum. For a star would be the hydrodynamic modes. Okay, but just using the usual EFT reasoning, we know that these multiple moments, just by dimensional analysis, they need to go like the mass of the object times its size to the L, where L is the multiple number, and similarly for these spin-induced multiple moments. Okay, so in the effective field theory, all of these different properties of the objects, of course a black hole is going to be quite different from a neutron star, are encoded in the correlations between these multiple moments. Okay, so this can be a purely classical theory, but there's going to be some correlation functions of this Q. I'm using here the notation of a quantum theory because it's more familiar for many of us. But for instance, if we take a look at the kind of retarded response of this thing, it's going to be a function of frequency, and it's going to have some low frequency expansion. So the leading term is the so-called static tide, also static love number, and then also dynamical corrections that tell you about the response of the object to kind of time-dependent fields. Okay, and the ones which are even in omega, they're conservative effects. Then the ones that are odd, they also have eyes floating around. So these effects encode dissipation. Okay, so this encodes both the kind of dissipative properties of the horizon, say things like absorption by the horizon of the black hole, or by the hydrodynamic modes of a star or a neutron star, the tidal deformations, how it behaves, what is the conservative response in an external field. And again, we can power count these coefficients, and they have some very simple power counting in terms of powers of the size of the object. And you can even integrate out these multiples and just write kind of point particle coupled to non-millimillimeter gravity, which encodes the same effect. So for instance, the leading coupling will be this lambda 2, which is a coupling to curvature squared on the word line. And you can also have the dynamical correction, which are time derivatives. The dissipation, you need to double the degrees of freedom, but you can also couple these things to this kind of nonlinear couplings to gravitational field. Okay? And similarly for the magnetic. Okay? Notice that this lambda 2, I told you that goes like mr to the 4. Okay? So this actually, for gravity, starts at pretty high orders. So I'll come back to that later. Okay, so this is a very simple effective field theory. Why might one care about this? Seems kind of boring, but next I'm going to tell you that there's something that one could use this EFT for everyone. Okay, so the first thing is actually for experiments. So we are probing now black holes and other compact objects in actual experiments in gravitational wave detectors. So we have a pair of these objects orbiting each other, eventually merging, that then we are going to detect on the Earth and in the space in about 10 years. And so this is the waveform, or kind of a idealized form of the waveform that we observed, say, at LIGO, Virgo, Cagra. And for most of this time series, for all of these in spiral phase, these two objects are far away from each other. So actually, we are precisely conserved with this regime where the frequencies involved are much smaller than the size of the object. The interactions between them are via kind of gravitons or gravitational fields whose frequency goes like the separation between the objects, which is much larger than the size of them. Okay? So for instance, this dynamics is sensitive to the so-called tidal love numbers. So this is kind of the linear response of one of these objects to an external field. So this leading coefficient tells you about the linear static response. I just put this object in a constant external gravitational field, and I ask, what is the induced quadrupole moment? How does it deform? Okay? And there's this very nice fact that in 4 dimensions, these static tidal responses, actually not only the quadrupolar, but for any multiple number, they're exactly 0. Okay? So this provides kind of an excellent window or possible window into new physics, because actually we know that we are going to probe these numbers in actual gravitational wave experiments. Even in the current generation of gravitational wave experiments, we're going to be able to put bounds on, pretty tight bounds on these tidal deformabilities of various objects. Actually, dynamical responses are not 0. And okay, we recently computed some of this using various ideas from scattering amplitudes. That's a topic for another talk, but you can ask me later if you're interested. And actually, as I said, this directly kind of modify the dynamics of these compact objects. So for instance, one can compute corrections to the Newtonian potential, which are kind of finite size corrections, tidal corrections, which start at this order in the 1/r expansion. So they're the so-called 5 post-Newtonian order. So it's 1/r to the 6 versus 1/r. And also they modify the flux of like the actual waveform, so the flux of energy, angular momentum at infinity. And thanks to that, actually some of my collaborators used actual data to put very recently the first bounds on kind of the dissipative tides. So this is a bound, it's centered around 0, so it's pretty small. They're not very tight bounds yet. This is using kind of various gravitational wave events. Okay, so this is just the beginning of a long story where we hope to probe things like the equation of state of neutron stars and many other kinds of physics that we're interested in. Okay, so that's the part which is related to experiment. Actually, still concerning experiment, I told you that the frequencies involved are, for the dynamics, are kind of order 1/r, but when we are observing gravitational waves from infinity, we are looking at frequencies which are much smaller than 1 the separation between the objects, okay? Because we are looking from very far away. So this is familiar. So we use the quadruple formula to compute the flux of energy from gravitational waves from some system. So actually what we do in practice is, again, we replace this whole binary system by a point particle with dynamical multiple moments, and then we compute the radiation from this point particle. Okay? So even the way that we compute the radiation from these binary systems is using this effective field theory. Okay, maybe you don't care about binary systems. Maybe you care about quantum black holes. Okay, so this EFT has been used also for some interesting applications in this context. So for instance, there was this paper maybe a couple years ago by Wald and friends that said that there's this very interesting effect where when you have a quantum superposition near the horizon of a black hole, it can decohere. Okay, so this seemed something very special, but actually there was a paper by Malacena and Biggs that argued using this point particle EFT, so if you just couple some qubit to this point particle, where you're releasing a black hole, and actually any compact object by this point particle EFT, these dissipative love numbers, they tell you about this response of these multiple moments, or any operator that describes the dynamic of the object, and in fact, this is responsible for this decoherence, okay? So this kind of demystifies these results, and it tells you that it's kind of a generic feature of quantum systems, okay? Goldberger and Roslin also used this EFT to study interesting effects that come from virtual Hawking quanta. Okay? So we are very used to think about the spectrum of real Hawking radiation in some black hole process, but actually they looked at what you would call like loops of this Hawking quanta at long distances, which is where this EFT is valid. But for instance, they found that if you look at the cross-section of some massive particles in GR, okay, there's going to be a quantum correction from this cross-section just from loops of gravitons. And actually, there's a correction comparable in size coming from virtual Hawking quanta. Okay? So if you want to compute these quantum corrections in gravity, you need to include these effects, and this EFT gives you a handle. I won't get into any of the details, but that's an interesting use. Maybe you care about holography. So a typical thing that people do in holography is they compare something like correlation functions of two heavy and two light operators, which in ADAs we compute by just throwing some heavy particle along a geodesic and interacting with some waves. And on the other hand, there's the thermal two-point function of this light operator, which we compute by thinking about the propagation of waves in some black hole background. And okay, at leading order, this in 1/n, these things agree, but actually for a generic heavy operator, which, most likely it's a black hole, but not necessarily, then one should see the difference between these two correlation functions at some order in 1/n. And actually, in principle, this EFT predicts where you would expect a breakdown, where you would expect to see the finite size of this object, which the effects might be different from a black hole or some other kind of particle. Okay? So this is just to motivate you to listen to the rest of the talk, where I will actually present some results. But even though it's a very simple EFT that we use since we threw kind of cannonballs and computed the trajectories in undergrad, I think there's still some interesting features. Okay? So let me tell you some of the predictions that this EFT makes. So the first thing is that there's some degree of universality. So the leading two couplings, they're coupling to the energy and to the angular momentum. Okay? There's no dynamical dipole in gravity. There's only this coupling to the angular velocity. So these are universal. Okay? So all the corrections go like starting at spin squared, or something that goes like r to the 5, size of the object to the 5, actually divided by g, but r to the 5 over g. Okay? So the EFT predicts that we actually won't be able to tell a point particle from a black hole or from any other object until very high orders in this low frequency expansion. Okay? So if we can only probe this low frequency regime, then it's very hard to distinguish, and that's why these point particle approximations work so well in practice. Okay? And similarly, if you want to study the effects of spin, you need to go to actually spin squared and leading order in the radius. Okay, another prediction for this EFT is that tidal coefficients will actually run. Even in classical GR, they're going to undergo renormalization group running. Okay, so the intuition for this is very simple, is that a compact object in a nonlinear theory, when you replace it by a point particle, well, it cannot be cleanly separated from its environment. You need to tell me how much of the gravitational field you're integrating out together with the object when you're going to the point particle description. And there's a dependence on this kind of cutoff radius that you choose. And the way you see this in the EFT is that it actually has UV divergences. Even classical GR coupled to a point particle has UV divergences. It's not a UV complete theory, it's non-normalizable. So some generic observable that you compute, say I compute in dim ray, is going to have poles, and renormalization, like these divergences can be absorbed in renormalization of these tidal coefficients, in particular of these dynamical tides. Okay, so there will be pieces of this running that will be proportional to the tidal couplings themselves that you can interpret as an anomalous dimension for these multiples, and there will also be a beta function that really tells us about the two-point function. Okay, so an example of such an object is the multiple form factor. So I'm looking at the one-point function of this multiple. I measure the gravitational wave that comes from it, and this actually will have anomalous scaling at low frequencies. Okay, so, and you see it explicitly in perturbation theory because there's going to be these logarithms at even orders in the G-Newton expansion. And they come from simple diagrams where you have multiples coupled to sources. So these are not loops, but because there's only energy conservation, not three momentum conservation, there's still integrals that one needs to do here, and there's UV divergences. Now, this is interesting because part of this anomalous dimension, actually most of it, all the pieces that depend on this leading coupling, so the leading part of the anomalous dimensions, it's actually universal. So it's actually a prediction from the EFT, and it tells you that it will be independent of the nature of the object. Okay, and they're almost the same for any object, and in particular, we could use any particular object to compute these universal pieces. Okay, so my talk is actually about this. About this anomalous dimension for these multiple moments. So the question is, okay, this is just classical GR. This is a classical RG. Hopefully we can make some general statements. Maybe it's easier to understand than more generic RG because we have some power. So I will try to present to you some formula, some exact formula for these anomalous dimensions, at least for black holes. So these are the two main results in a paper to appear soon with my collaborators. The first one is that we derive some nice relation between this anomalous dimension for the multiples and the phase shift for scattering against these compact objects. So if I ask you, what is the anomalous dimension of a multiple? Then you ask the question, okay, let's just scatter some spherical wave with the same multipolar number from the compact object, compute the phase shift, construct this linear combination kind of at positive frequency, and then analytically continuing the frequency. A here is the spin length of the object. I won't say much about it, but it also works with with spin, and then you take this combination, and that gives you the anomalous dimension. This formula is general. It's valid for any compact object. But then for a black hole, we can do better. And actually, a black hole in particular captures these universal pieces of the anomalous dimension. And there's a nice formula that relates this anomalous dimension to the quantum A period of some particular cyber-Witten theory, which I'll explain in a second. So this is a mathematical equivalence. I don't think there's any physics between this, but it's some technical statement. So let me explain this in some detail. Okay, so first let me explain where that formula comes from, and let me review how this works in usual setting of particle scattering, not in QFT. So there's this beautiful paper by Simon Cranvoud and Matthias Willem where they explain to us how to compute renormalization group running from the S matrix. So the idea is we take F is some form factor of some local operator. We take the local operator, we act on the vacuum, we overlap it with some on-shell state of particles, and then this object satisfies this nice relation. So the anomalous dimension is actually something like the face of the S matrix. And the derivation basically just uses analyticity, dimensional analysis, and unitarity. Analyticity is if I analytically continue the signs of all of the momenta to negative sign, this just gives me the complex conjugate at this position. But actually, by scaling, I can just write this in terms of the dilatation operator acting on the complex conjugate form factor. And then unitarity tells me that from unitarity, if I perturb by this local operator, I can derive this sort of relationship. Actually, here I'm missing an S dagger on the right-hand side for this form factor. I'm putting them together. It tells you how to compute, say, anomalous dimensions in terms of unitarity cuts. Okay? So what we do to extract this is a very simple and very similar type of argument. Instead of looking at the one-point function of this thing, we're going to look at the two-point function to just kill the beta function contribution. So we're going to look at this symmetric two-point function of this operator, which is the multiple coupled to the gravitational field, which is roughly the imaginary part of the retarded Green's function. And the same kind of moves, just using analyticity, dimensional analysis, and unitarity, we can prove precisely that this anomalous dimension is related to the face of the S matrix, and because we're looking at the two-point function here, we have two copies of this face. Okay, so this is the magic equation that we could use actually also for some binary or something, and I'll comment about this at the end where I explain some application. But now I need to tell you how I compute this for a black hole, because we actually want to use this formula in an example. We're going to plug in the phase shift for a black hole. Okay. So what does the scattering amplitude for scattering some wave of a black hole look like? Well, let me partial wave expand it. So this is scattering against a curved black hole. There's some mildly complicated partial waves, and there's the usual scattering amplitude. There's an absorptive part, it's eta. There's a scattering elastic scattering phase shift, delta. And this phase shift receives contributions from kind of two regions. One is the so-called near zone, which is the region near the horizon of the black hole, which encodes all of these finite size effects. It encodes the knowledge of these log numbers, et cetera, et cetera. There's also the far zone piece of this phase shift, which is actually what the EFT knows about. This is kind of what the scattering very far away from the object. Okay, so how do you calculate this? We just need to solve kind of linear perturbations of this black hole with wave boundary conditions. So we look at the so-called Tulkowski equation, which is, okay, we look at the wave equation in the black hole background. We multipole expand it. Sorry, we partial wave expand it. We separate variables. There's some magic how this happens in 4 dimensions, but you get some radial equation that looks like this. And then you have 3 singularities at 0, 1, and infinity. 0 and 1 are regular. At infinity is irregular. You plug in incoming boundary conditions at the horizon, and then you read off the solution at infinity. The ratio of the kind of growing and decaying part is precisely this scattering amplitude. Okay, and actually this question of imposing boundary conditions here and reading them off at infinity for this kind of differential equation with this singularity structure is the so-called question of the connection coefficient for the confluent-Hoyne equation. Confluent-Hoyne equation is a differential equation with 3 singularities, with one of them being irregular. Okay, so traditionally this was computed just doing kind of match asymptotic expansions between the far zone and the near zone, but a couple years ago there was this very beautiful paper by Alba Grassi and her collaborators where they pointed out that actually this radial Tulkowski equation is exactly equal to the quantum curve of some particular cyber-Witten geometry. So if you take SU2 n equals 2 super Young mills with 3 hypermultiplets with these identifications between the parameters of the gauge theory and the gravity. So the masses, some of them are related to the spin and to the perturbative parameter. The instanton counting parameter is related, again, to g omega. Chi is just the spin, essentially. Okay, so there's some dictionary. This is a mathematical equivalence. They're just the same differential equation. But then we can just unload all the machinery that has been developed in the context of supersymmetric gauge theories to solve this equation. And in particular, there's this whole technology of Nekrasov-Shadapishvili functions, or also by AGT, like semi-classical Liouville conformal blocks that actually provide a full solution for this problem. Okay. So, okay, this was done in this paper by one of my collaborators, and this is the result. This is what the far zone phase shift looks like. So there's so-called Coulomb phase, it's a divergent part. There's some complicated stuff, Tolkowski-Starorinsky constants. This is where the Nekrasov-Shadapishvili function shows up. There's some kind of Sommerfeld piece. But I want to draw your attention to this last term here. So this last term is written in terms of something called the renormalized angular momentum, nu, which had appeared since 30 years ago in the GR literature. No one knew what it was, but the people perhaps were inspired, and they called it the renormalized angular momentum. Well, you can check that this thing is precisely the quantum A period for this hyperwritten geometry, which again we can compute sort of combinatorially from these NS functions. Okay, there's also some formulas that you can get for the near zone phase shift, but I won't show it because it's not relevant. And voila, if you plug in this formula for the phase shift in this relationship to extract the anomalous dimension, everything cancels except for this last term, and we get that this anomalous dimension precisely replaces the ordinary angular momentum, or the ordinary multipolar number, by this renormalized angular momentum, which is precisely this quantum A period. Okay? And this we can compute to very high orders. We can compute it essentially to any order perturbatively, and we can even probe its structure numerically using this mathematical relation kind of non-perturbatively, and try to understand the features of these anomalous dimensions. Okay? Okay, and to end, I will explain an application, an actual prediction. So I told you that one use of this anomalous or this EFT is to actually describe the radiation from a binary system, which is what we measure at LVK. And in particular, we can use it to actually resum logarithms in the waveform, in literally the observable that we observe in LIGO. So this is the spectral waveform, not in the time domain, but in the frequency domain. And then we can predict that there's a bunch of logarithms that will be resummed as a power of this anomalous dimension. And for quasi-circular binaries, which is what people usually study, then we can propose this kind of formula that resums many of the logs. So there's some piece here, which is the part that we cannot resum. But OK, so this is the anomalous dimension. This is kind of the part that comes from the infrared divergence, the 1 over r Newtonian interaction. This is kind of a Sommerfeld enhancement factor. Actually, this also follows if you use this cyberwritten technology to directly compute this anomalous dimension, to directly solve for the radiation from a Bohr line. So this is the probe limit, where one of the objects is much smaller than the other. Then you find a very similar structure. So this is a non-trivial check of this formula. And we can check. We can just go to the results that people have computed perturbatively and check if we can resum part of those. And OK, everything that appears here in the box, we were able to resum using our formula. There's additional logs that we cannot resum because actually they have to do with other physical effects, so-called non-linear memory effect, and which is actually not captured by this anomalous scaling of the multiples, at least not from the universal part. And actually, we've checked that this holds for many other multipolar numbers. Okay, so I think this is a pretty strong check. So I will end with that, and I won't bore you with a list of conclusions. I'll just say that I think, in my opinion, this is a nice example where there's a lot of knowledge that actually originally comes from the string theory community, the study of scattering amplitudes and analytic properties, try to understand them using unitarity, causality, et cetera, has its origins actually in string theory, or maybe they're kind of intimately connected. And I think the same is true for the study of supersymmetric gauge theories. And I think when combining this knowledge with very general considerations of effective field theory and normalization group, we were able to provide actual predictions for real-world experiments. Okay, thank you very much for your attention.
Thank you. Questions?
Thank you. Very nice talk. The connection between the cyber within quantum curve, which is what we see in topological strings, with the problem that you were trying to solve in the GR, suggests that maybe there are other aspects of that which enters here. And in particular, my question is, in that context, there's the importance of Fourier transform. You choose a frame to write your answer, so the wave function undergoes Fourier transforms.
Mm-hmm.
What would that, if any, would mean on the GR side?
So the wave function is actually the wave that we are computing here, right? So I think the Fourier transform, I mean, it depends what you mean by the Fourier transform on the
Flipping A and B periods.
Yeah, actually I think this is not understood. It's a bit hard to tell because as far as I know, this correspondence is a purely mathematical correspondence. So we can use this dictionary, but it's not clear a priori that some physical question and physical operation on one side will correspond to a physical operation on the other side. However, let me say that actually the B period is precisely what captures this near zone physics, and for instance is what gives you some exact quantization condition for the quasi-normal modes, which are living in kind of the part of the amplitude that I didn't describe. And actually this was used also in some very nice paper by Sasha and Alba Grassi and Matt Donaldson and friends, where they use it to study precisely this question of like thermal correlation functions in ADS, where there's a similar, here it's like the regular Hoyne equation or the confluent Hoyne equation, but there's a different cyber-Witten geometry in which you can kind of play the same games, and there this B period played an important role. Actually, well, it's what you see, what you would call the B period from the flat space that they're switched, but anyway, they both play a role, but I'm not sure about the Fourier transform.
Hi.
Hi, Atle.
Since you alluded to it, what kind of imprints do the equation of state of neutron stars leave on these tidal deformation coefficients? And maybe a slightly out there question, can the interiors of black holes also leave some imprints on their tidal deformation coefficients?
So the coefficients are just different for these objects, right? So for instance, the leading tides, the static tides for black holes are 0 in 4 dimensions. For neutron stars, they're not 0. And I told you that they modify the potential, they modify the flux. So you could just, in principle, directly ask, is this correction to the potential 0? Can I put a bound on it? And you would just see it. Now, if you ask me for particular equation of state, okay, this is just one number. Okay, so if you look at the whole pattern of these tides, presumably you could distinguish the different equations of states. But more generally, these tides, and in particular the running, they're related to so-called memory effects, so-called tail effects, which is that the gravitational waves that we see, they actually have a memory of the past of the system. Right? You think that the dynamics in principle is instantaneous in time, but this running tells you that there are kind of logarithmic corrections to that. So there's actually a memory of the state of the system, which I think has many implications. Yeah.
Thanks. So about this, like a two-point function generalization of like a Caron-QO and a Wilhelm that you used.
Mm-hmm.
I understand that you're using it for the classical physics, but can you get something that applies to general quantum field theory?
Yeah, I think in principle one can play the same game. Here it was very easy because we just had the frequency to understand the analytic structure of. If you have a generic two-point function depending on two momenta, I think in principle it might be a bit harder to understand the analytic structure and to derive a similar thing. But for this kind of point particle theory where we just have the energy to worry about, it seemed like a very natural thing to do.
Sorry, thanks for the great talk. I'm curious about the interplay between these theoretical methods and the simulations, both of GR and of neutron stars and so on. Does this sort of extend the range before you have to start doing those simulations and you input a new initial condition or something like that?
Yeah, so it's very complementary because, for instance, okay, I don't have this plot in this talk, but numerical GR works very well when you have things like comparable masses, aligned spins, et cetera, et cetera. But for instance, as soon as you have, say, the masses of the two objects being a ratio of like 10 or higher, actually I think the highest that people can do is up to 30. But for instance, for LISA, for future space detectors, we're going to be studying things like neutron stars orbiting supermassive black holes at the center of a galaxy, where numerical GR just does not work. Of course, numerical GR provides you the full answer, this whole waveform, when it works. And, and then for these setups, actually, the final predictions are some like phenomenological models that combine this analytical data that tells you about this very long in spiral phase, which very high accuracy, with kind of numerics for the merger, and then say for the normal model theory for the ring down. But I think some people think that, oh, because you can just put GR in a computer, we are done. That's definitely not true, because numerics only works where you don't have strong hierarchies, but actually we do in the events that we'll be looking at.
Yeah. Shiraz.
In the large D limit, a black hole can be, the equations of motion of a black hole can be reformulated as a membrane with a velocity field living on it.
Mm-hmm.
Now your expansion in multipole seems to me to be more or less expansion of the shape of that membrane. I was wondering if this velocity field plays any role. It's a very, very big question.
Yeah, actually I think this is something that I thought about a lot, because I think this membrane in principle encodes more information than this point particle description. So it's actually an intermediate EFT, which sits between full GR with a horizon and everything, with the interior of the black hole, or with hydromodes of your neutron star, and this point particle description. But I think, except in the large D limit, this membrane paradigm, I think it's a nice physical picture, but it's not a systematical tool. And I think, yeah, maybe also in holography it is a systematical tool, but for black holes in flat space that we observe in the real world, I think it would be extremely interesting to make your question precise. I've tried without success so far, but I think it's a very important question. And by the way, it might also illuminate this question of the vanishing of these static tides in black holes, which I think, even though there are several proposals of symmetries, to me at least, it remains mysterious. Yeah.
So your result for exact anomalous dimension has this poles in spin, and is there understanding what dictates the structure and what is the interpretation of these poles?
No, but so it does have poles at low values of angular momentum when you expand it in perturbation theory, and we don't know what those correspond to. Of course, the poles appear whenever you have this running, as you might expect, but yeah, no, but it has many tantalizing features. In addition to that, you can study kind of numerically its dependence on the frequency, and you see that, okay, it's real, and then when you hit the frequency corresponding to the size of the photon sphere, crazy things happen. So I think it's very interesting to study the analytic structure of this object, both as a function of the frequency and angular momentum, and I think there's a lot to be learned from it.
Okay, let's thank Julio again. And I think we'll restart 11:30.